Application layer. Fieldbus access sublayer. Fieldbus access sublayer is a part of secure communication. Since Fieldbus does not have layers 4 to 6 between DLL and APL, FAS directly maps APL requests to DLL services. This is the most important part of VCR management. The FAS provides 3 communication models for applications. Client-server model. The client-server model is universal and used in many communication technologies. An application called client requests another application called server to do a specific action through FMS. When the server finishes the requested action, its result is transferred to the client. This communication takes place at any moment. Publisher-subscriber model. Publisher-subscriber model is designed to link function blocks. When a publishing function block runs, its output data is stored in the buffer of the publisher VCR. Then the LS sends CD to the VCR to force it to transfer the data in DT-PDU. Subscriber VCRs receive this PDU and give the data to the subscribing function blocks. Source sync model. The source sync model is designed to broadcast messages. It is one-to-many one-way communication without schedule. This model is sometimes called report distribution model. A source VCR transfers a message in the queue to an assigned global DLSAP address when the device has the token. Sync VCRs have the same global address and receive the same message from a source. Fieldbus message specification. Fieldbus message specification, FMS, is a service interface for user applications to use Fieldbus services. When a service is requested, it encodes the request to transfer it to the other applications. The receiving FMS decodes the request to notify the application. Virtual Field Device, VFD. A Fieldbus device may have user applications which are independent of each other and do not interact. A Fieldbus device consists of virtual field devices for such individual applications. An identifier given to a VCR identifies the VFD. A Foundation device has at least 2 VFDs. One is the management VFD where network and system management applications reside, and the other is a function block VFD where function blocks exist. FMS objects. Applications in a VFD are shown to other applications on the network using an object model, which consists of attributes, behavior, and access methods. Examples of objects include function blocks, alarms, and schedules. An object is identified with a number called index, which is unique within the VFD. Additional information to describe an object is called the Object Dictionary, OD, which is an assembly of information called object descriptions to explain the objects. FMS services. FMS provides various services to access FMS objects, including variable access, event management, domain management, and program invocation. Examples of these services are variable access, services to read, write, and report values of variables. Event management, services to report, acknowledge, and monitor events. Domain management, services to upload and download continuous memory areas. Program invocation, services to manage data processing functionalities. Other services include OD management services to read object descriptions and context management services to manage connections between applications. TAP System Management Protocol, Tag and Address Assignment. A field device is identified with its PD tag as well as its node address. System Management Kernel Protocol, SMKP, provides services to assign them to a device. When a device changes its address, it disappears and comes back to the link with a different address, making its behavior complicated in the data link layer. A special protocol is defined for this purpose to manage such transitions effectively. Tag location, device tag, and function block. Tag are useful for humans but need longer data for communication. SMKP provides services to replace device tag and block tag with node address and index to simplify further communications. This mechanism ensures that devices and function blocks can be accurately and efficiently located within the network, facilitating smooth operations and management. Application time synchronization. Fieldbus applications need to be synchronized in the sense of time to interact with each other effectively. For example, an event message needs a timestamp to indicate when it is detected because it is received sometime later, depending on the token rotation and bus traffic. SMKP provides a mechanism for all management VFDs to share the synchronized time. This ensures that all devices and applications within the Fieldbus network operate in a coordinated and timely manner, which is crucial for maintaining the integrity and reliability of the control system. High-speed Ethernet. Why Ethernet? Ethernet is one of the most popular networks for office and business applications. Network components such as cables, hubs, and switches are available at very low prices from the commercial off-the-shelf environment. Its media are evolving very quickly, with 100 Mbps Ethernet replacing traditional 10 Mbps Ethernet, and even faster Ethernet of 1 Gbps emerging. It is better to utilize those COTS components both in cost and availability. Ethernet's popularity and cost-effectiveness make it an attractive option for high-speed Fieldbus applications. TCP/IP Protocol Suite. The TCP/IP Protocol Suite is the de facto standard in the information technology IT world. When Foundation Fieldbus goes over TCP/IP, it makes it possible to open the door to the IT world and build a total network from the plant floor to the enterprise level. IP, Internet Protocol, used to transfer data to a desired station IP address. Foundation Fieldbus utilizes IP version 4 today and will switch to much more powerful IPv6 in the near future. TCP, Transfer Control Protocol, provides connection-oriented transport services that can be used for client-server communication. UDP, User Data Protocol, transfers an amount of data to a desired application and can be used for source sync communication. Publisher-subscriber communication can use either TCP or UDP. SHAST, Field Device Access Protocol. It is desirable to have the same applications for measurement and control regardless of their physical location in a hierarchical network. FMS and SMKP services must be maintained for this goal. The Field Device Access, FDA, protocol is designed for this purpose to allow all FMS and SMKP services to go over TCP/IP. This ensures that the same measurement and control applications can be used seamlessly across different parts of the network, facilitating efficient and coordinated operations. Virtual field devices in a Fieldbus device. A Fieldbus device may have user applications that are independent of each other and do not interact. A Fieldbus device consists of virtual field devices, VFDs, for such individual applications. VFDs can be seen as different field devices from an application point of view. Communication services guarantee their independence. A Foundation Fieldbus device has at least two VFDs. Management VFD, where network and system management applications reside. It is used to configure network parameters, including VCRs, as well as to manage devices on a Fieldbus. Function Block VFD, where function blocks exist. It is possible for a field device to have two or more function block VFDs. Function block. What is a function block? A function block is a functional model common in measurement and control. It is a generalized concept of the functionality you have in field instruments and control systems such as analog input and output, as well as PID control. The Foundation Specification, Function Block Application Process Part 1, gives fundamental concepts, while Part 2 and later give various function blocks details. Function block parameters are visible and accessible through communication services, and the block behavior depends on the values of parameters. A function block may reside in virtually any device on the network, and a set of function blocks connected to each other to form an application can reside in one device or be distributed among devices. The function block VFD contains three classes of blocks: resource block, function block, and transducer block. Link and schedule. A measurement or control application consists of function blocks connected to each other. These connections are made through link objects in the function block VFD. A link object connects two function blocks within a device or a function block to a VCR for publisher or subscriber. The system management and data link layer cooperate to orchestrate the execution and communication of function blocks even when blocks are distributed among devices. The system management in a field device starts function blocks according to the function block schedule. The LAS transmits the compel data CD PDU to a publishing device to force the output data to be transmitted according to the LAS schedule. These two schedules, function block schedule and LAS schedule, are defined as offsets in the control period called macro cycle and must be configured to schedule function blocks and communication in a desired order. Parameters. A block has a series of parameters that are accessible by choosing one with an FMS index. Parameters of a block have continuous indices. Parameter classes. Output parameters. An output of a function block that can be connected to input parameters of other function blocks. Input parameters. An input of a function block that can accept one input parameter of another function block. Contained parameters. Neither input nor output, accessible only through on-demand read or write request. Parameter attributes. Access write. Parameters can be readable and or writable. Dynamic or static. Dynamic parameters vary with block execution, while static parameters do not vary and may be written by on-demand request. Status of a parameter shows whether the value of a parameter is useful or not, good, bad, or uncertain. Important parameters. Several parameters are common to many blocks and are very important. Block mode, mode BLK. All blocks have their mode, expressed by this parameter. It is a record of 4 components: target, actual, permitted, and normal. The mode can be one of OS, man, auto, CAS, RCAS, and route. Scaling parameters. Some function blocks need scaling of the data as 0 to 100%. A scaling parameter is a record of 4 components: EU 100%, EU at 0%, unit code, and point position. View objects. A function block has many parameters, so it is not practical to read them one by one for display purposes. Foundation Fieldbus utilizes the FMS variable list concept for this purpose. A view object is a predefined variable list made of many block parameters. 4 view objects are defined for each block. View 1 operation dynamic. List of dynamic parameters necessary for running the plant by operators. View 2, operation static. List of static configured parameters that may be necessary to show operators along with the dynamic parameters. View 3, all dynamic. List of all dynamic parameters that may be used for detailed display or diagnosis. View 4, other static. List of static parameters that may be useful for configuration and maintenance purposes. Important blocks. AI block analog input, AI block, is designed to allow users to enjoy a standard model of generalized signal conditioning functions. An AI block receives data measured by the transducer block and manipulates it for scaling, square root calculation for an orifice plate, low-pass filter, alarm generation. Scaling and square root calculation, L-type parameter, controls scaling and square root. PV, process value, determined by L-type. XD scale provides 0% and 100% value of channel value in its engineering unit. Outscale provides 0% and 100% value of the output value. Low-pass filter PV time parameter, time constant for the low-pass filter in seconds. Alarm generation, low limb, low limb, HI limb, high limb parameters define alarm thresholds. Permitted modes, OS, man, and auto. In man mode, you can modify out value. In auto mode, PV.value and PV.status are copied to out value and out status, respectively. Channel value, channel parameter, chooses one of the data values from the transducer block. The channel value is visible in the simulate parameter. Simulation, simulate parameter, allows AI block to use simulate value and simulated status as channel value instead of transducer value and transducer status when enabled. AO block, the analog output AO block, is designed to allow users to enjoy a standard model of output devices like a valve positioner. An AO block receives the control value from a control block and sends back the current control value so that the control block can calculate the next control value or track the current value if the AO block is not controlled by that control block. The proportional integral derivative block is designed to provide standard PID control functionality. The PID block receives process variable inputs and output control variable to regulate the process according to the PID algorithm. PD algorithm, proportional P, integral I, and derivative D components. These components work together to regulate the process by adjusting the control output based on the error, the accumulated error, and the rate of change of the error. Control parameters, gain, reset, rate parameters, define the behavior of the PID control. Resource block and transducer block. The resource block and transducer block provide foundational functionalities for field devices. Resource block, device information, manufacturer's name, device name, and other relevant information. Hardware status provides status information about the device hardware. Control controls the overall device hardware and function blocks within the VFD. Transducer block, sensor and actuator models, provides a model for sensors and actuators. Measurement principles, models specific to different types of measurements, such as pressure transmitters and magnetic flow meters. Channel parameter links the transducer block to the function block through the channel parameter. Recommended values. Recommended values for various applications are provided based on Yokogawa's long experience in measurement and control. These values can be used in most cases. Example applications. Simple measurement, AI1, the transducer block gives measured value in the desired unit. Scaling in AI, AI2, the transducer block gives measured value in a unit and AI block converts it into another unit. Orifice plate flow meter, AI3, the transducer block gives measured differential pressure with an orifice plate, and AI block converts it into flow rate by calculating the square root of differential pressure. Unit codes. Unit codes are essential for defining engineering units for scaling and parameter values. Important unit codes include GPM, gallons per minute, psi, pounds per square inch, inches, other relevant units. Unit codes ensure that values are correctly interpreted and displayed in the appropriate engineering units.